Okay, welcome to lecture here. Do that maybe. So again, make sure you put here in the chat box for roll. And we're going to continue on with chapter 1 and then probably roll into chapter 2. Again, the notes can be found in the module section up there on Canvas if you need them. Just get a couple of things out of my way here. Do that. Okay, so last time we kind of started talking about chapter 1. We talked about really the atom, sort of the structure of the atom, some really important sort of experiments that led to our understanding really of the structure of the atom. Again, the atom basically being made up of our protons, which are positively charged, found in the nucleus, along with our neutrons, which are have no charge, basically, also found in the nucleus. And we do have the atom basically sort of proven there by Rutherford's experiment, the gold foil experiment, that it mostly was empty space. It had that really dense positive core, which is our nucleus, where, as he just mentioned, our protons and neutrons are found. And traveling out from some distance from the nucleus is our electrons, again, traveling in sort of a random pattern. They don't travel in pretty circles, pretty random about the nucleus. They're traveling. As we also talked about, there is some attraction between the nucleus and those electrons. Again, electrons being negatively charged, our nucleus essentially being positively charged. And that's, again, as we'll talk about in later chapters, some of the reasons why certain electrons are involved, say, in things like bonding. Other electrons are not involved in bonding. We also talked about sort of those three subatomic particles: protons, electrons, and neutrons. Protons being positively charged, electrons being negatively charged, and neutrons have no charge. The heaviest of all three of those is the neutron, followed very closely by the proton. And the lightest of all of the particles there is our electrons, which also is why we sort of figured out there that most of the mass of the atom, again, is the nucleus, which contains both neutrons and protons, and each of them are about 1,800 times heavier than any sort of electron that's basically flying around. Any questions on any of that stuff we sort of talked about last time? So we're going to kind of continue on here in chapter 1 and finish talking about a couple other things about atoms and some important aspects of atoms, which are the atomic number, the mass number, and what isotopes are. So I think we'll start out maybe with isotopes. Isotopes, again, are essentially the same element, but they do have different masses. And what makes them sort of have different masses is actually that they have different amounts of neutrons, and different number of neutrons will give them different masses. But again, they are still really the same element. Because they do have the same number of protons, as we will see. Protons are really important in terms of, what element you're talking about. Again, the protons basically determines the element that we're dealing with. And again here, something like, say, copper, I think maybe I wrote last time, 64 versus copper 68. They're both copper. They both will have really the same number of protons. The difference, though, which is this number here, comes from really the number of neutrons. Because they are really the sort of same element, they will have very similar chemical properties. And that's because pretty much most reactions or chemical reactions we deal with really deals with electrons and what happens with electrons. They either gain, they're lost, they're shared. And that's in normal chemical sort of reactions. That's usually, really the subatomic particle involved. We don't really deal with anything in terms of protons, neutrons in normal chemical reactions. When we deal with nuclear reactions, we talked about a little bit last time as well, and you'll talk more about in 200B. You do actually change things like protons and neutrons, but most naturally sort of chemical reactions really involves those electrons. So here's an example again of sodium. And this sodium again has 11 protons, also has again 11 protons on this side. And this guy again would be the same element because the number of protons are the same. So that tells us they are the same element. The difference here is one has 12 neutrons in the nucleus, one has 13 neutrons. In this case, actually both still have 11 electrons in both cases. And that's what gives us our difference here. This is sodium 23, also sometimes written like this, sodium 23. And this is sodium 24. Again, the difference is the one neutron difference between the two. So that brings us to a really important number when we talk about sort of atoms, and that is the atomic number. And the atomic number is sometimes abbreviated with a Z. And the atomic number is the number of protons that you find in the nucleus of an atom. So it is the number of protons. If a atom is neutral, and as we talked about, since really an atom contains protons which are positive, electrons which are negative, and neutrons which have no charge. If we have something that's neutral, that means all the positives and all the negatives should equal each other, which means if you have something that does not have a charge, the number of protons will also equal the number of electrons, so that all the positives and all the negatives really balance each other out. The actual identity of an atom can be determined by the atomic number. We could actually, if we go to the periodic table, we could find the atomic number on the periodic table. So for example, if you look at a periodic table and you have hydrogen, and there's a number up there on top, which is 1. And there's a number on the bottom, which is 1.008. This number up here on top is the atomic number. So the atomic number can be found on the periodic table. It is typically that number found above the symbol. So if we look at something like nitrogen, 7N and 1401. Again, the 7 is the atomic number. We look at something like neon, which is number 10 there. And 20.18. Again, the number up on top, which means if I have a neutral hydrogen atom, it would have 1 proton. It would also have 1 electron to balance it out. Again, positive and negative balance each other out. And you could definitely identify somebody by its atomic number. So if we look up nitrogen here on the periodic table, we will see the number 7 above it. And again, that tells us automatically that nitrogen has 7 protons. And if it's neutral, it would also have 7 electrons. If you look at the periodic table for all those atomic numbers that are in the boxes, all the numbers up on top, there is not a number that repeats. So every single element has its own atomic number, which means if you know the number of protons, which means you know the number of, the atomic number, which is the same thing, you also will know what element you're talking about. So that's a very important piece of information that you can get from the periodic table, the atomic number. Now, sometimes people get a little confused with sort of this part of it, that the atomic number will equal the number of electrons in a neutral atom. It is very important to understand that if you are asked a question like, what is the definition of the atomic number? The actual definition of the atomic number is just the number of protons. So that is the actual definition of it. The second part to that is it will tell you in some cases the number of electrons, but the number of electrons is not the definition of atomic number. It is solely just the number of protons. Any questions on that there? So another important number is what is referred to as the mass number. And the mass number is, excuse me, the mass number is the number of protons and the number of neutrons that you find in an atom. So we have our mass number, which is our number of protons plus our number of neutrons. We have our atomic number from the previous slide, which is our number of protons. And why the mass number is important is if you take the mass number minus the atomic number, protons will cancel, and that will give you the number of neutrons. So we can basically figure out the number of neutrons that are present by taking the mass number minus the atomic number, and obviously that will give you your number of neutrons. Now, when you're asked to calculate something like that, the number of protons, the number of electrons, the number of neutrons, the mass number, and the atomic number, those all should be positive whole numbers. So they all have to be whole numbers. Can't have like a half an electron or something like that. So it's got to be all positive whole numbers. Now, every single element has protons, electrons, and neutrons, except for our good friend hydrogen. Hydrogen only has a proton and an electron. That's pretty much it is. It has no neutrons. Every other element will have protons, electrons, and neutrons, but hydrogen is a little bit different. Hence why you sometimes will see hydrogen in weird places on the periodic table on both sides, but does not have a neutron. So we know that when we look at the periodic table, for example, for something like hydrogen, we do know, as we talked about previously in the last slide, that the atomic number can be found there. And that is our top number. So the question is the bottom number the mass number? Well, based on our definition here that the mass number, along with everybody else, needs to be whole numbers, that is clearly not a whole number. And if you look on the periodic table, all the numbers pretty much underneath the elements, they're not whole numbers. There are a lot of decimal numbers. So important is this number that we see on the bottom of the periodic table is not the mass number. It is what is known as the atomic mass, which we'll talk about in a later chapter, but it's actually the atomic mass of the element. So really important that on the periodic table, the only number that you can find is your atomic number. So again, you can find that on your periodic table. You will not find your mass number, not on the periodic table. Any questions on that there? So isotopes, as I talked about earlier, again, are elements that are substances that are basically the same element. They do have those different numbers of neutrons, which makes them different. And oftentimes when we do write sort of a symbol that includes the atomic number and the mass number, we write it in sort of in this format. So we have our element symbol. On the top left is where we put our mass number. Bottom left is where we put our atomic number. So these are all examples of isotopes. We have hydrogen, we have deuterium, which is heavy hydrogen. We have tritium, which is radioactive version really of hydrogen. And we could write sort of this symbol for each of them. So hydrogen, if we weren't sure what the symbol was or what element we're dealing with, we could look at this number and we see one proton. You would go to the periodic table, you would see number one is hydrogen, which is H. The atomic number would go bottom left, which would be 1. Now the mass number is, again, the guy that goes up on top. So in the case of that, that would be 1 proton plus no neutrons equals 1 for the mass number, which would go up there on top. And that would be the correct symbol for hydrogen with our mass and atomic number. Looking at our deuterium, even though it has a different name, it still has 1 proton. So going to the periodic table, one proton is still hydrogen, still means it has an atomic number of 1. But now when we get to our mass number, we have 1 proton and 1 neutron, which gives us a mass number of 2. So again, that would be the symbol for deuterium. Lastly, here we have tritium. Again, even though it doesn't specifically say, hey, this is hydrogen, we know it really is hydrogen because when we look at it, we see 1 proton. 1 proton, again, going to periodic table, going to give us hydrogen with an atomic number of 1. Mass number here going to be 1 plus 2 gives us 3. And that would be the symbol there for our, excuse me, tritium, which again is sort of the radioactive version there of hydrogen. Question on mass number, atomic number, how to write the symbols correctly. Any questions on any of that there? And again, as I sort of wrote one a little bit earlier, this is again a very common way that we sort of write isotopes, but just as common, we write something like, say, carbon 64. And when we see something written like carbon 64, you may wonder again, what is that number? Well, one thing that we would know for sure is we are dealing with, I said carbon, copper, I know it's copper, copper 64. We are dealing with copper. And if we look on the periodic table for copper and not carbon, copper is 29 right about there. And we have something like 65, 39. No, we got 63, 55. 63, 55, something like that. So one thing we know for sure, if we did go to the periodic table, copper's atomic number would be this guy. So clearly that 64 is not the atomic number. It should be 29. So what the 64 actually is the top number there. It is the mass number. So that's a very common way. Again, yeah, I'd say copper 68. That means the mass number here would be 68. So that's, again, another very common way that sort of isotopes are written. Any questions on that there? So why don't you try a few here? So take a minute or so here. We want to know how many protons, electrons, and neutrons there are in each of the following. And we'll talk about the answer here in just a second. Mass number, which again is our number of protons plus number of neutrons. Bottom number, again, is our atomic number, which is our number of protons. So that's a pretty good place to start. Our number of protons in this case should be 27, which is the atomic number. Now, this thing does not have a charge, CO, which is cobalt. We know it doesn't have a charge because if there was a charge, it would be written right about there. So we don't see anything written there. So no charge. No charge means that it is neutral. So since it has 27 positive guys, it would also need to have 27 negative guys or electrons to basically balance that out. That leaves us really our number of neutrons, which is the mass number minus the atomic number. So really the top number minus the bottom number. So our number of neutrons would be our mass number, which is 60, minus our atomic number, which is 27. It's a lot of math there, but I can go with 33 in that particular case. Any questions on where any of the numbers came from, how we determined any of that? Okay, looking at the second one here, which is Cl, which is chlorine. Again, we don't see any type of charge written there, so we assume that is neutral. Looking at the bottom number, we do see that our 17 is our number of protons. Again, just like we just talked about, because it is neutral, That also means we should end up with 17 electrons in this particular case. And lastly, here we're looking for a number of neutrons. So our number of neutrons would be our mass number, which is our top number, 37, minus 17, which is our bottom number. And I believe that is 20 in this particular case. Any questions on that there? And lastly here, that's U, which is uranium. Again, I don't see any type of charge written there. That means looking at our atomic number, which is 92. Number of protons here going to be 92. Also, our number of electrons will match it because it has no charge. And our number of neutrons in this case is a lot. That is 238 minus 92, blah, 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 146 maybe on that. Give or take a few here, maybe 146. Sounds like a winner. Any questions on any of those ones there? Okay. So why don't you try a few more here? I think here we want to know what is the symbol, right? The symbol for krypton that has 48 neutrons. The other one you have is we have the nitrogen atom with 6 neutrons. And the last one is, I believe, iron has a mass number of 56. What is the number of protons, number of electrons, and number of neutrons? So take a moment here and then we'll talk about it. So we want to write the symbol with the mass number and the atomic number for each of these and see what you come up with. Let's see how we're doing then. First off, we want to go with krypton. So the symbol for krypton is number 36 there on the periodic table. So it would be Kr. The 36 that we see on the periodic table on top is the atomic number, which should go there on the bottom. And that also tells us that it has 36 protons. And that's important because it tells us it has 48 neutrons. And both of those together will give us our mass number if we add them. And if we add those together, that looks like 84 in terms of our mass number. And really, that should go up there, up on top. Any questions on this one? Obviously, it doesn't say anything about a charge, so we could assume that's neutral. So if we were curious, it should also have 36 electrons to balance it out. Looking at nitrogen, again, if you go to periodic table, you see nitrogen is N. Also from the periodic table, you can see the atomic number is 7. It's the atomic number. And again, that's going to be our number of protons. That also is going to be what goes up there on the bottom, or down there on the bottom, I suppose. It has 6 neutrons. So if we add our 6 neutrons to that, that will give us a mass number of 13, which should go up on top. Any questions on that symbol there? And lastly, here we have iron, which has a mass number of 56. Looking at the periodic table, the symbol for iron is Fe. The 56, which was given to us in the problem, is the mass number, which should go up on top. From the periodic table, we can see that Fe on top has a number of 26. That would also tell us that in terms of the number of protons, it is 26. In terms of the number of electrons, it is 26. And our number of neutrons going to be our mass number, which is 56, minus our atomic number, which is 26, going to get us 30 neutrons in this particular case. Any questions on that? Any questions on writing something in terms of atomic number, mass number, or figuring out protons, electrons, neutrons? Any questions? Okay. So you may be asking, what happens if we actually do have something, that does have a charge? How does that affect, sort of the numbers and stuff like that? So first off, if we do have something with a charge, those are what are referred to as being ions. So ions are things with charges, basically. So they're charged entities. And there's really two types of ions that we deal with, as we talked a little bit about last week as well. There's the cation, which are positively charged guys. And there's also anions, which are negatively charged. So in this particular case, let's just take, say, our nitrogen here. And if we took our nitrogen, that was 13 and 7, and we gave it its normal charge of -3. So what we want to think about is maybe what is changing here that we have the -3 charge. Well, if we look at it, first off, we know it's nitrogen, and we know that the atomic number is going to be 7. That means that the number of protons we have is 7. In this particular case, the number of neutrons would actually be the same. That's going to be our 13 minus 7, which would give us 6 neutrons in this case. So it's clearly not the neutrons, it's clearly not the protons that is different. It is actually the number of electrons in this case. And in this particular case, it would actually have 10 electrons. If you take 10 negatives and add them to 7 positives, you are left over with a -3. And that -3 is where the charge comes from. So the -3 that we see here comes from that difference in the number of electrons. So how did the electrons change from our neutral guy over here? Well, from our neutral guy, it also had 7 electrons in this particular case. So the number of electrons went up. It went from 7 electrons in the neutral case to 10 electrons in the charged case or the negative case. And the charge here that we see, the -3, is how many electrons it gained. So when something becomes negatively charged, it is usually a result of gaining electrons. The number of electrons gained from the neutral guy is equal to the actual charge. So again, if something has a -3 charge like here, it gained 3 electrons from the neutral guy. If it had a -2 charge, it gained 2 electrons from the neutral guy, and so forth. Any questions on that one there?
Can you explain where you got 10 again from?
Yeah, so we know that it has to have 7 protons, right? Because it is still nitrogen. And
Right.
because the atomic number is 7, it's got to stick with those 7 electrons or 7 neutrons. Let me say that right. 7 protons, because if it wasn't 7 protons, it would be some other element. So that locks really us into place in terms of having 7 positive charges.
Mhm.
The neutrons here are the same, and neutrons have no effect on the charge because they're neutral. They have no charge at all. So it has to be the electrons to get us to basically -3. So if you just think about, 1, 2, 3, 4, 5, 6, 7 positive charges, in order to leave us with 3 negative charges, if you just kind of draw them in there, you need 10 of them, right? So this guy here, for example, if I could get it, change color real quick. Go with this. So this positive guy is done with this negative, right? This positive balances out that guy. This one balances out this guy, balances it out, plus a negative equals 0, balances it out. And now we're at a positive. So what we end up with is really 3 extra negative charges. And the only thing that's negative in the atom is electrons. So that's how we went from 7 electrons to start with in the neutral guy. We had to end up with 10. That gives us that kind of leftover -3 that we end up with in terms of the charge, which basically means that it gained 3 electrons here. Does that make sense? Questions on that?
Thank you.
You're welcome. Other questions on that? Okay, so let's take a look though what happens so if we do sort of the opposite thing here, which is it gains something with a positive charge rather than a negative charge. So let's just say we took our iron here, and again here we'll go with kind of the same thing. So we'll go iron 56, 26, and let's just go with a +2 charge in this particular case. Now, again, the same idea here, because it's still iron, it still has 26 protons. And if we wanted to our neutrons here, it's still 56 minus 26, which gives us 30 neutrons, just like we had before. So same idea, it is the electrons that actually change when we gain a charge. And in this particular case, he will end up with 24 electrons, 26 positive guys, and 24 negative guys will leave you that +2 charge that's left over. And again, we see that in the neutral, it started with 26 electrons, the guy that had no charge over here. When it did gain a charge, like we see over here, it actually ended up with 24 electrons. That is 2 less than it started with. So the charge here is 2. The number tells you how many electrons. The plus here tells you that it lost electrons. So this guy would lose electrons, and that's how something becomes basically positively charged, is by losing those electrons. Questions on that? So in this case, we actually have more protons than electrons, and that's essentially what is giving us that positive charge that we see here. So when we're dealing with something that has a charge and we want to figure out protons, electrons, and neutrons, again, it really is just the electrons that change when that occurs. So why don't we take a look at one here, maybe. So let's just say we had, let's do, what do we want to do? Let's do this guy here, Mn4 plus, and let's just say it is 25, and we'll go with 56, and let's do let's do phosphorus with a -3 charge. And in case you don't have a periodic table, we'll go 15, and we'll do 32. So take a minute or so here and figure out the number of protons, electrons, and neutrons in each of them. And if you like, when you're done, you can type them into the chat box. That will kind of get an idea where everybody is. Trying to see some answers roll in, so let's see how we're doing just to make sure. So we'll start with the one on the left there, which is Mn, manganese, and let's take a look at what we got going on. So again, it does give you some information here. We do have the atomic number given to us, which is 25. And again, if it wasn't given to us, we could go to the periodic table and we could really find the number there. And in this particular case, that means that this guy would have 20, let's borrow this, 25 protons, which are positive. In terms of neutrons, we would subtract those two. So again, we would take 56 minus 25, and that's going to give us 31 in terms of our neutrons here. Now that leaves us our number of electrons. Here we see a positive guy, which tells us it's a cation. Also tells us it lost electrons. And the number of electrons it lost from the neutral guy would actually be 4. And it is positive, again, telling us that it lost it. That means that this guy should end up with 21 electrons, 25 positive guys plus 21 negative guys is going to leave us that +4 positive charge left over on that particular one. Any questions on that first one there? Now, looking at the second one, again, we could kind of dissect it as well. We got the 15 given to us. And that is our atomic number, which again, we could find on the periodic table. Our neutrons, we could subtract these two numbers here. So number of neutrons would be 32 minus 15. That's a lot of math there, but I'm going to go with 17 and hope for the best on that. So that's 17. Here we do see a negative, which tells us automatically that it gained electrons. Also see a 3, which means that it should have gained 3 electrons from the neutral. We know actually just looking at our atomic number that the neutral guy should have 15, which means if it gained 3 electrons here, it should actually be 3 plus the atomic number, which would give us 18 electrons, giving us that minus 3 that is left over. Any questions on how to figure out charges here? Electrons, protons, neutrons.
Can you redo
Yeah.
MN? Because I'm having trouble understanding the electron part.
Yeah. So for Mn, it has a +4 charge. And again, really what the plus means is the plus tells you in the charge that it lost electrons.
Hmm.
Or basically tells you how many it lost, right? And how many it lost in this case, because it's positive, we're talking about from the neutral sort of element. So the neutral element, if we just look at the neutral element, which is Mn, we know that it has 25 protons, just like this guy does. And in the neutral guy, if it had no charge, it would also have 25 electrons, right? So in this case, we know that it lost 4 electrons from it, the neutral. So it has to end up with 21 electrons to go with our for sure 25 protons there are. And again, if you just add like 25 minus 21, right, that gives you +4 basically. And that's where the charge comes from. Again, it has basically 4 less electrons. So as I did with that other example where I drew all the positive, all the negatives, in this case, if you drew all 25 positives and you drew all 21 negatives and you kind of matched them up, paired them up, you would be left with 4 positive symbols there, which represents the 4 sort of protons that are left over that really don't have negative electrons to sort of balance them out.
And then the neutrons is 31, right?
The neutrons would be the same in this case because the mass number is the same. So the mass number is 56 and the atomic number is 25. So again, by subtracting those, that actually stays the same. So really anything, and neutrons really won't have an effect on the charge because again, they have no charge themselves. So remember that what we talked about with the atom. In the atom, there's really only 3 things, right? There's protons, which are positively charged. There's electrons, which are negatively charged. And then we have our neutrons, which have no charge. So in terms of things that have the ability to affect the overall charge, it can never be the neutrons because they just don't have a charge to begin with. And because these things are like the same element, the proton number is pretty much locked into place because that's really the one that determines what element you're dealing with. So it has to only be the electron as the thing that could really affect the charge. And if it's positively charged, it means it lost electrons from the neutral element. And if it's negatively charged, it means it gained electrons from the neutral element. And how many it lost or gained is equal to the actual number that you see. So something with a +1 charge meant that it lost 1 electron from the neutral. Something with a -1 charge meant that it gained 1 electron. Something with like a +12 charge, which you'll never see, meant that it technically would have lost 12 electrons from the neutral guy. Other questions on that? Other questions on this in general? So obviously you do need to be able to write these symbols correctly, showing the mass number and the atomic number. You also need to obviously be able to figure out how many protons, electrons, and neutrons there are. And lastly, obviously, you need to be able to do this with things with either positive or negative charges. Any questions on any of that stuff there? Okay, so we're going to finish up here chapter 1 with a talk a little bit about energy. And again, we don't really talk a lot about energy in this class, which I think is, I want to say chapter 6 in our book. They moved it to Chem 200B, where you'll really kind of officially talk about energy. We'll hit upon some energy along the way in certain places, and we'll talk about it in those situations, because as you could probably imagine, the book assumes that you probably read it from, first chapter to last chapter. So they assume in later chapters that you already talked about energy. So we will touch upon energy along the way, but we're not going to go into tremendous detail about it, but we'll kind of, brush up on things that sort of relate to other topics that we're talking about. And again, you'll get sort of a formal lectures and on energy when you get to Chem 200B. So things like specific heat that you maybe talked about in Chem 100 and stuff like that, we really don't get into in this class. We sort of skip over it. But just a little bit about sort of overall energy. Energy is really the ability to do work or produce heat. Work is really some type of force is acting over some type of distance. Important thing to remember about heat and energy is that it does flow from really a hotter object to a cooler object. So heat and energy is transferred that way. The hot guy gets cooler, cooler guy kind of warms up. They happen to be sort of in an insulated container. They would sort of meet probably somewhere there in the middle in terms of their temperature. Law of conservation of energy, as we may touch upon earlier in this chapter as well. Again, there's no real creation or destruction of energy, but energy does really transfer from sort of one location, if you want to think about it that way, to another. And what that really means is, if something gives off energy, so for example, if you do a chemical reaction, or like strike a match, for example, or something like that, right? The heat and energy that's maybe given off from the reaction is going to be equal to the heat and energy that would be absorbed by, say, the surroundings, everything outside of the reaction. And vice versa, if a reaction was a reaction that basically absorbed heat and energy, it would pick up all that heat and energy from the outside. So same idea, like if you heat up an ice cube, right? Or just an ice cube, you take it out of the freezer, it's going to pick up all the heat and energy from the surroundings. So the surroundings, the air and everything's losing all that heat and energy. The ice cube is basically picking up all that heat and energy. So there's sort of a constant energy content in the universe. It just does go from one sort of spot to the next. There's actually sort of a difference as well when we talk about a little bit about some types of energy, the idea between temperature and something known as thermal energy. Temperature is sort of a measure of sort of the motion of the atoms and stuff like that. Thermal energy is a result of how many atoms or molecules are present. So that's why, for example, if you had a cup of water or something like that at, say, 90 degrees Celsius, and you had a giant, say, bathtub, that's 40 degrees Celsius. The bathtub actually does contain more thermal energy than, say, that cup of water or coffee or whatever it may be. And that's because obviously in the bathtub, there's a lot more water molecules moving around, a lot more thermal energy associated with that, even though in a sort of a smaller context, there's less molecules moving around, but it's in a smaller area, which would give it a higher temperature. So sometimes people think, again, that both of those things are really kind of the same thing, but there really is sort of a difference between sort of thermal energy and sort of the meaning of temperature. And one, again, is associated with the motion of those sort of molecules and stuff like that. Here are some of the energy, we talk about radiant energy, again, coming from the sun. Thermal energy, as I just mentioned, is really associated with the random motion of atoms and molecules that are present. Chemical energy, there's energy that are stored within sort of the bonds of molecules and stuff like that. So for example, if I had a bond I would need to put energy in to break it. When I put energy in, everybody gains energy. They kind of wiggle apart. If I want to make a bond, everybody's moving around fast. I need to remove energy from those guys. They kind of slow down and they're able to sort of come together to make a bond. So there's a lot of energy involved in those type of processes as well. And we actually will get into a little bit of that when we talk about bonding and sort of bond energy and the energy required to make bonds and break bonds. So that's something we kind of touch upon in this class. Nuclear energy is the energy is stored within basically the protons and neutrons in the nucleus. So one thing that we've been talking about is the idea that in normal chemical reactions, we really don't do anything with the protons or neutrons. And that is definitely not the case in nuclear chemistry. We actually do change protons into neutrons, neutrons into protons. So we change basically the center of the atom there, the nucleus. And obviously, as you can imagine, that takes a lot of energy associated with really changing those subatomic particles, and it usually results in a lot of energy. That's why nuclear reactions oftentimes will give off a lot of energy associated with it. Potential energy is your classic sort of energy that is based on sort of the object position. Classic book example, right, is the big giant boulder that's on top of the hill contains a certain amount of potential energy above the poor guy standing on the bottom of the hill. And potential energy can be changed into kinetic energy as the big boulder goes over the hill and starts rolling down. It's going to change from potential energy to kinetic energy until again it hopefully doesn't, but it lands on hopefully not the person and maybe just the cement there. And when it hits the cement, it's going to transfer that energy to the cement. And again, it will come to rest at a new potential energy, different than where it was way up on top. When it comes all the way down, it will hit there. Now, when we talk about energy, there's a couple of terms that maybe you're familiar with or you've seen before. And again, one is Q is the symbol we sometimes, or the letter we sometimes use to represent heat. So that's a very common sort of guy. But a lot of times we also will represent energy and reactions with the delta H, and that is what is known as the enthalpy. And that is a very common sort of way that we represent energy in sort of reactions, is by the delta H value. It could be thought of as sort of the overall energy associated with sort of a reaction happening. And really, there's two types of reactions that we oftentimes would see. One is an exothermic reaction. And exothermic reaction means that heat and energy is released. So whenever you have some type of process where there's heat or energy released, that's what's referred to as being exothermic. Two ways that we usually represent that is either with Q or delta H, and how we know just by looking at those values if it's exothermic is it is typically a negative number. So if you're given the delta H for a reaction or even the Q value for some type of process, it basically is telling you the number is not truly important in a lot of cases, but the sign is important. So you see that negative, it tells you that you're dealing with an exothermic reaction. And opposite of that is what is known as a endothermic reaction. So in an endothermic reaction, heat and energy is absorbed. And that's kind of like the ice cube example. The ice cube is picking up all that heat and energy from the surroundings. That's an endothermic process. And we also see that for endothermic processes, our Q value, our delta H value, again, for our purposes, the number not extremely important, but the number typically will be a positive number. So again, if you see a delta H value given to you, and you see that it is a positive value given to you, then you know that that sort of process is endothermic and heat and energy is being absorbed. Any questions on that there? So a couple other things about energy that will pop up along the way as as we sort of continue through. The amount of kinetic energy, which is sort of the energy of motion. Again, if you want to calculate the kinetic energy, we probably won't use this formula very much anywhere, but it's half the mass times the velocity squared. But one thing that we will sort of see along the way in some calculations, and maybe even the next chapter, is a relationship in terms of some important units. And one important unit is a joule. And that's what the J stands for, is a joule, which is a very common unit of energy. A joule has a relationship, as it shows on this screen here, of being equal to a kilogram times a meter squared divided by a second squared. So that relationship between these two, we definitely will see, and I think we'll see it in the next chapter, if I'm not mistaken. So again, that's an important sort of unit relationship to remember. A couple other important ones. Joules is a unit that we commonly see. Kilojoules. Calories with a lowercase c. Kilocalories is also another very common unit. And there is a difference when we talk about sort of lowercase c and capital C. When we talk about capital C for calories, that is actually sometimes referred to as a nutritional calorie. So a nutritional calorie, one of those nutritional calories is actually equal to 1,000 of the little calories. And that is the same as 1 kilocalorie. So you sometimes will see that when you talk about sort of energy and nutrition. You look at like, food nutrition labels, or if you're on a treadmill or some type of exercise equipment, they'll sometimes tell you how many calories you burned or how many kilocalories you burned. So that's something that we see a lot as well. And I sort of touched upon some of that just there, but again, the definition of a calorie is actually the amount of energy that's really required to raise 1 gram of water by 1 degree Celsius. And that's also, if you maybe remember specific heat capacity has a very similar sort of definition. It's basically the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. Here's some common sort of conversion factors. And again, we're not going to get into a lot of energy, but when you take 200B, for example, this is one that this relationship is used a lot to go from one unit to the next. All right. Any questions on that? That should wrap up pretty much chapter 1. Last thing to touch upon is sort of something that we did talk about earlier, I think, but just to remind you again, we have sort of the idea of opposites attract. That again is something was referred to as a electrostatic attraction, which means that if you have a positive guy and a negative guy, they are attracted to each other. Also means that if you put something that is positively charged near something that is positively charged, they are repelled by each other. And if you put something that is negative by something that is negative, it also will not want to be near each other, and they will go opposite of each other and try to move away from one another. So very important sort of interaction in terms of charges and stuff like that is this attraction between positive and negative guys. It is, as we'll see when we get to the bonding, as you may know, we talked a little bit about, is the basis of really ionic bonding, which is that positive cation together with our negative anion. Any questions on chapter 1? Okay, so give me 1 sec here and we will roll to chapter 2 here. Just get it queued up, I think. All right, so chapter 2, we're going to kind of continue on talking about a little bit about our atom. We're going to mainly talk about really one part of the atom for the most part in this chapter, and that really is our electrons. So in this chapter here, we definitely will be dealing with electrons, what's going to happen to electrons. And a lot of it is sort of that basic idea of what we were talking about in the lab last week. And that's the idea of, for example, why we see something like our different colors here with our fireworks. And ultimately, what happens is pretty much what we sort of talked about. It's the idea of our electrons, basically, right? And we have our electrons at our different energy levels. And obviously, when you shoot off a fireworks, there's a certain amount of, say, explosives in there. When it explodes, right, it obviously is going to allow those electrons to gain a lot of energy and again work their way up to sort of this higher energy level. So as it works its way up to that higher energy level, as we talked about last week, pretty much everybody wants to be in a lower state of energy. So because things want to be in a lower state of energy, this electron is eventually going to want to work its way sort of back down to a lower state of energy. And as we talked about with the flame test, it's basically the same idea. That energy, because we do have that conservation of energy, will be given off a lot of times in the form of a wave with a specific wavelength. Now, again, as we talked about with our sort of flame test, if this wavelength sort of hits in that visible part of the spectrum, we'll see colors. And as you saw with the flame test and that first experiment, there are different elements, and different elements have different numbers of electrons. They're at different energy levels, and they do sort of different types of transitions when this occurs. And that's really why, we do see different colors, say in our fireworks and stuff like that. And again, it really does has to do with our different elements that are present. Again, certain elements only have certain numbers of electrons. If you're talking about something like carbon, it's only got 6 electrons per se. Then something like oxygen that has 8, something like neon has 10 versus argon that has 18 electrons. And again, these electrons are going to start out at different energy levels. So as they get excited, those electrons bounce to higher energy levels and come down. When you're comparing, say, something like, for example, neon versus argon in terms of colors, neon again only has 10 electrons, which means it's going to max out at a certain sort of starting period in terms of electrons, while argon, which has 18 electrons, has 8 more electrons, which are going to end up being higher in energy probably to start with. So it's going to get some different transitions that we might not see in neon. Same thing with hydrogen. Hydrogen has kind of 1 electron, which will allow us some different sort of transitions that will occur just with that 1 electron that is present. Come here, there we go. So what happens with electromagnetic radiation? We're really talking about waves. So we sort of touched upon waves in lab, but just to reiterate some of the parts of waves, waves basically have 3 different sort of characteristics associated with it. One is the wavelength, so it's sort of how far it is from one peak to another peak on a wave, one trough to another trough. And again, what we're talking about with electromagnetic radiation is it's basically the movement of energy through space, basically. Drew a much better wave than I did the other day. In the really the form of a wave. So as this wave is moving, there's a certain amount of energy associated with it. As we talked about a little bit as well in lab, it's based on the wavelength, also the frequency as well. Frequency, as we'll talk about again, is how fast sort of our number of waves that pass a particular point in a certain period of time. The speed of the wave is also really sort of important as well. So let's take a look at each of these a little bit more in depth here. Again, our wavelength, which is lambda. I'm not sure why the lambda symbol went way off course there, but the lambda symbol there, it's actually right there, I think, is the wavelength. And again, that's that distance as we go from peak to peak or trough to trough. Probably should use the one I just drew, but we'll use this one here. So when we talk about the wavelength, again, that sort of distance between the peaks or even the troughs, if you will, come in this direction, is our wavelength. The frequency, again, it's not really a V, it's a nu. people oftentimes call it a V, but it's actually not a V, is represents the frequency. And that again is the number of basically waves that pass through a particular point in a given period of time. When we talk about the speed of a wave, sometimes C is used, and C is the speed of light, and it is 2.9979 times 10 to the 8. I personally round, so I go with 3 times 10 to the 8 meters per second, since most of that will probably get rounded off anyways. So 3 times 10 to the 8 meters per second is the speed of light, basically. And again, that is abbreviated with a C. And that gives us sort of an important relationship, as we will see. You could take the speed of light is equal to the wavelength times the frequency. And if we just sort of look at the units of these guys, the unit of wavelength is typically meters. The unit of frequency is reciprocal seconds, 1/seconds. So the frequency in terms of units is 1/seconds, or reciprocal seconds. And a reciprocal second is the same as a hertz. So that is a relationship that we see a lot, especially when we talk about frequency. Again, a reciprocal second is the same as a hertz. Now, if we just look at these sort of units, that gives us the units that we see for the speed of light of meters per second. So that's common units that we see. This is an important little sort of formula. It allows you, again, if you know the wavelength, you could figure out the frequency. If you know the frequency, you could figure out the wavelength, again, because C is a constant. Kind of the same calculation, depending on whichever one you're looking for. The wavelength would be the speed of light divided by the frequency. Again, is one way you could rearrange that. Or if you were looking for this, the frequency, it would be the speed of light divided by the wavelength there in that particular case. So those are a couple different ways that you can sort of rearrange those formulas and use it. And those are ones that we will use in some calculations here. So you do want to make sure that you keep track of it. Any questions on that there? So again, important, a couple of things off of this slide just to make sure. Obviously, this formula, the speed of light is a constant value, the relationship between those two things, and obviously how to rearrange these equations, really important as well. Any questions on that there? All right, so why don't you give one a go here and see what you come up with. Calculate the wavelength of red light with a frequency of 4.62 times 10 to the 14 reciprocal seconds. Let's calculate the wavelength in nanometers. See what you come up with. Reminder that nano is 10 to the -9. So see what you come up with here. When you're done, put the answer there in the chat box, so I have an idea where everybody's at, and we'll talk about it here in a couple minutes. See what you come up with. Times 10 to the 14 reciprocal seconds. That means that we do want to use the formula that we just saw on the previous slide there. The relationship of C is equal to the wavelength times the frequency. In this case, we always have C. C again is that 3 times 10 to the 8 meters per second. In this case, we also have the frequency given to us, which is 4.62 times 10 to the 14 reciprocal seconds. That means that we do want to solve for the wavelength. So if we did that, the wavelength there would equal C divided by the frequency. Again, bringing the frequency to the other side and dividing. That would give us 3 times 10 to the 8 meters per second up on top, divided by 4.62 times 10 to the 14 reciprocal seconds. So really important at this point to take a moment and talk about how to properly enter these numbers into your calculator. So first off, a reminder, and again, if you know this, that's good. If you're not sure, this will be a good review. Whenever you put a number in your calculator in scientific notation, you want to make sure that you actually use your exponent button. So on a lot of people's calculators, the exponent button will be a button that is like EE. Some people will have a button that looks like EXP. Some of the newer calculators will have an actual button that is times 10 to the n. Now, if you do have one of these newer ones, you want to punch it in exactly the way I'm going to kind of tell you, except that you do need to put parentheses around every single number that you put in the calculator in scientific notation. Otherwise, your calculator will probably program it and do it wrong. So how would we put something like 3 times 10 to the 8 into our calculator correctly? Well, you would hit 3. You then would hit your exponent button. So the EE button, EXP button. And if you have a calculator with that button, it probably will put a 3 and an E, or it may put a 3 and pop up a couple of zeros or something like that. When you hit that exponent button, that button does represent the times 10 part of the number. Remember, scientific notation is something like this. And that means that this part of the number here, you don't have to punch it in, which means you shouldn't hit the multiplication button. You shouldn't be hitting like the second log button, inverse log, none of those buttons. The next thing that you would do is actually just put an 8 because it's a positive exponent, and it would probably pop something like that. Or if you had the bottom one, it would change the bottom one to like an 08. If you have, again, this button here, you need to do the same thing. You just got to open a parentheses. You need to hit 3. You need to hit that button times 10 to the n. When you do that, you will see something on your calculator like this, times 10, and then the cursor will be blinking up here. You then need to put 8, which will then give you 3 times 10 to the 8 that's blinking. Then on this calculator, most of them have like a little circle kind of guy. And you need to hit the circle on the right-hand side, and that will bring your blinking guy down and then close the parentheses. So if you do have some of those newer calculators with that button, you pretty much need to punch it in like that. Make sure you put parentheses around every single number. Obviously, at this point, we would punch the next one in the same way, divided by 4.62. Again, exponent button, 14, and obviously the equals button. And if you do all that good stuff correctly, and you want to make sure you always use that exponent button, you will end up with something like 6.49, excuse me, 6.49 times 10 to the minus 7 units. Seconds cancel, leaves us units of meters. First off, any question on that part of the calculation there? Okay, so hopefully you got that number, but again, the units here are meters, so we need to use this to convert it into nanometers. And I will say most of the time people will screw this part up. What that means when you see something like nano is 10 to the minus 9, that's how much there are in the base unit to one of the prefix units. That means in this case, we're dealing with nanometers. So in 1 nanometer, there is 10 to the minus 9 meters. Can't tell you how often people reverse those two and end up with the wrong thing here. So when you see that 10 to the minus 9, 10 to the 3 on like a prefix table, that's how much there is in the base unit, which in this case is meters, to one of the prefix units. Any questions on that? So that's what we want to use to finish out this calculation, because we're in units of meters, doing a little dimensional analysis, opposites cancel. That means 10 to the minus 9 meters on the bottom, 1 nanometer up on top. So we're basically taking that and dividing it by 1 times 10 to the minus 9, and that will give us 649 nanometers as our answer, which if you remember from the lab last week, that's somewhere in the red region, I think. Any questions on any of those steps? Really, really important. Make sure you always use your exponent button when you type something in scientific notation. It is where a lot of people make some bad mistakes. You know, usually that you are probably not punching it in correctly, because when you look at a number like the one we got here, usually when you look at the front part of the number, it's all good. But when you look at the exponent part of the number, if you're punching it in wrong, not so good. You're usually off by 1 or 2 or something like that. And that's, if that's the case, or you see that's the case with some of these calculations, because we will be using our exponent button a lot in chapter 2 here, it's probably the way you are punching that in. So if you're not sure on your exponent button, make sure you take a moment to try to figure it out. If not, make sure you take a moment and ask me, probably in lab is a good idea. And we'll try to figure it out together. But those are the 3 common exponent buttons that you find. Any questions on that? Okay, so we're going to wrap lecture here right now. So what's scheduled for today in lab is experiment 2, which is about the stuff we're talking about. But honestly, we did not get far enough. So what I think we're going to do is we're going to continue lecturing actually on chapter 2 for just a little bit. And I think what we will do is we will move experiment 2 to Thursday. So we're just going to kind of lecture to get us back on pace, since we didn't do a lot of lecturing on that very first day. And that will allow us at least to have done some of those calculations that you're going to need to do in experiment 2. So experiment 2 will be moved to Thursday. We're going to continue lecturing on chapter 2 here.